we go. Looking ahead, our next test is in a week and a half or so. April. Goodness, we are on the doorstep of April already. It's crazy. This next unit, it covers two things, and two things that are very different that you have not done before. And so they're not hard, but they're definitely new. And so you guys that like to not pay attention and just coast and hope you figure it out later, that's probably not going to work this time. Like, this is very new stuff. And so, again, as long as you pay attention, you'll be fine. But that alone that's a high bar for some of you. So just leave it at that. All right, looking at the notes, parametric equations. Again, new stuff. Some people are going to like this because it's different and, I don't know, interesting to some people. Up to this point, you've been representing a graph by a single equation involving two variables, meaning things like y equals 3x minus 4. Right? That's a line that starts at -4 and has a slope of 3. Or y equals x squared minus 5. Right? A parabola that started down 5. Something like that. Like, that's what you're used to graphing. That's almost all of our graphing has been up till now. In this section, we will study situations in which it's useful to introduce a third variable. 3D. Not 3D, though. That's a good question because, yes, if you go far enough in math, you can do x, y, and then like z comes out of the plane like that. That's not what this is. That's harder to do. It's really hard to draw a 3D thing. That's not it. So it's a third variable, but it's still a curve in the plane, so not 3D. We normally let this third variable be t, and we usually think of it as time, so t for time. And we'll set up a pair of equations. This is not what parametric equations means, but that's sort of pair equations. They come in pairs. There'll be two of them. X of t will express the horizontal, right? The horizon stretches left to right. That's x, left and right. Y will express the vertical position, the up and down position. And then here's one thing that's new. We'll use arrows on the curve to denote the direction the path is taking as t increases. So it won't just be a graph, it'll be a graph that has direction. Like, it'll have a starting point when t is 0, or when t is -3 or whatever, and we'll put some arrows on it. Alright, so this seems really weird, but it works out. It's not really that hard. Consider the curve in the xy plane with position given by x comma y, where x is this equation, t squared minus 4. I could even add that to our table here. X is t squared minus 4, and y is 2 minus t. So we're going to make a table of values, but normally our table of values is, right, just x and y. We pick some x's and plug them in. But now we've got this extra variable t. We'll pick some t's. We'll plug the t into x to get the x coordinates. We'll plug the t into y to get the y coordinates. And then we'll graph the x and y. So like when we get to the end of the table, it becomes a regular graphing problem. Just graph x and y like normal. But getting x and y is the new part. So rather than just picking x's and plugging them into y, we're picking t's, plugging them into x and a y. All right, so let's do this. So -3. If t is -3, -3 squared minus 4, 9 minus 4 would be 5. And I think it's probably easiest, like we won't do this when we graph it, but for filling out the table, it's probably easiest to find all the x's first. That way you're working with one equation, and then find all the y's. That way you're working with one equation. I think it's less likely to get confused. All right, if I plug in -2 for t, 0. -2 squared is 4. 4 minus 4 is 0. I plug in -1. 1 minus 4 is -3. Plug in 0. -4. Plug in 1. I get -3. Plug in 2. I get 0. Plug in 3. I get 5. There's sort of a pattern going on there. I don't. It kind of flips across. It feels like a parabola, and of course it feels like a parabola because there's a t squared there. Sometimes you'll pick up on patterns. Sometimes the patterns are so sort of obscure you don't pick up on them, and it's fine either way. Let's do the y coordinates. So if I plug in -3, 2 minus -3, excuse me,
Wow.
2 minus -3, 5. That's what you meant to say. 2 minus -2 would be 4. 2 minus -1 would be 3. 2 minus 0, that one I can do. Speaking of patterns that you pick up on, I think I figured this one out.
Will they always start with the same number like that, or is it just like coincidence?
Start with the same. Oh, they start both at 5?
Yeah.
That's just coincidence. Yep, just coincidence.
Which is the variable that cannot repeat for it to steal the equation? Is it the x or the y?
Oh, like to see if it's a function?
Yeah.
It's each x has to have a unique y. So this is not a function because, right, if the input is 5, I don't know what the output is.
Okay.
So it's not a function, y is not a function of x.
Okay.
X and y are both functions of t, though. So that's why we don't really get into that because of that. That's a good question, and it also won't pass the vertical line test when we graph it. So that will become obvious in a minute. All right. When it comes to graphing, I don't need t's anymore because t isn't on my graph. This is an xy graph. So I don't even need the t's. I can just graph the x and y. So now this is like back to 7th grade, 8th grade, just plotting points. So 5, 5. 0, 4. -3, 3. -4, 2. -3, 1. 0, 0. And 5, -1. So it does, you guys were thinking like parabola or something repeats. Well, it is
Something.
It is a parabola, like a sideways parabola. And then what we also need to include is like which way it's going. So you have to kind of pay attention to, where did this start? Well, it started at 5, 5, and then went to 0, 4, and then went to -3, 3, and so on. And you don't really need an arrow in between every spot. That's a little bit overkill. But for the first one, that sort of emphasizes that we started up here when t was -3, and then t -2, and so on.
We don't draw like arrows as the we just draw the end one is not the end.
Oh, you mean like the arrows at the end?
Yeah.
You can. I guess it didn't really specify, so I guess I'd be okay either way. It's a good question. Actually, I'd be careful about that because if you drew an arrow this way, that would be misleading.
Yeah.
So let's only graph what it asked for. And a lot of times t will start at 0, and so you'll have like a starting point for the graph. Excuse me. Thank you. All right, part C. Find the rectangular equation, meaning y equals some function of x, by eliminating the parameter. Like get rid of t. So let's solve for t. So start with x, solve for t, plug it into y. That way you'll have y equals something. So let's start with the x equation. And let's solve that for t. So what should we do to solve that for t? I'd move the 4 over. I guess you could move the t over, but then you'd really have to do some fixing. So let's move the 4 over. So t squared equals x plus 4. And then what do you want to do? Square root both sides. I added the 4, but then I switched the sides. So what do you need to remember to do when you put the square roots on there? Plus or minus. So t equals plus or minus square root x plus 4. Y equals 2 minus t. So now I know what t is. I'll plug it in. Plug that expression in for t. 2 minus plus or minus square root x plus 4. That looks a little bit weird, so I'm going to write that as two separate ones. So 2 minus square root x plus 4 and 2 plus square root x plus 4. So we come back to that question you asked earlier, Jesus, about this being a function or not. It's not a function in terms of y and x because it's a vertical line test. And this sort of further explains it. It's like, well, if I know my x, I don't know my output because there's two different outputs. Right? And it took two equations to describe this thing. That minus one is probably the bottom half of the parabola, and the plus one is the top half of the parabola. So kind of weird, kind of different, but not really that hard. Just make a table of values, plug the t in for x, plug the t in for y, and graph what you got. The new graphing part is the arrows on there to indicate a direction that we're going. Part D. When t equals 10, what is the horizontal position of the curve? So, like, how am I going to answer that? What am I? That's all it's asking. Horizontal is x. So this just means x when t is 10. 10 squared minus 4 is 96. So it's not hard. It's just making sure you recognize, what's going on. Horizontal versus vertical. So the vertical position is -8. And that's it. You could graph that, except that you'd have to have a really big graph to get out to 96, -8. All right, number 2. Similar, just different equations to mess with. Consider the curve in the xy plane with the position given by x equals that square root and y equals that absolute value. Complete the table below. Be careful here. The t's seem like they're random. They're not. They may seem it now. Let's plug them in and see what happens. So if I plug in -1 for t, what do I get for x? I get the square root of -1. What's that equal to? I, if we really want to be, correct. Imaginary. It's not a real number. So it's not going to show up on my xy plane because this is the real number plane. There's no imaginary numbers there. So that's kind of weird, but that just means it won't show up on my graph. All right, if I plug in -3, and again, rather than going x, y, x, y, x, y, I'm going to do all the x's and then all the y's because I think that's easier to keep up with. Plug in -3, 0. Plug in -2, I get 1. If I plug in 1 for x, I get square root of 4 is 2. If I plug in 6, I get 3. And now I see why they picked these numbers. They're not so random after all. They're making me get nice square roots over here. All right, let's plug in y. Some people really mess up their absolute value stuff here. -4 minus 3 is -7, and then the absolute value is 7. Right, don't apply the absolute value till you get to the end. -3 minus 3 is -6. Absolute value, +6. -2 minus 3 is -5. Absolute value, +5. Be careful about pattern recognition, because it's like, oh, look, I see the pattern. Like, well, yeah, except that the numbers for t start being random, so don't just fill in 4, 3, 2 here. Plug in 1. 1 minus 3 is -2, but that becomes a +2. I can plug in 6. 6 minus 3 is 3. 13 minus 3 is 10. And it's not on here, but it would have been nice. Let's put an extra column, and you'll see why in a minute. Let's add an extra row to our table. Now, this makes the x be ugly. Square root of 6 is, I don't know, 2 point something. But the reason I picked t to be 3 is, what does it make y? 0. Okay, so let's plot those points, although can't really plot that first one. It's not that it's wrong. Is that park in your spot? Stole Miss Tip's parking spot. It's way out there. There's plenty of blanks or empties. She'll be fine. Let's see. 0, 6. 1, 5. 2, 2. 2 point something, comma 0. So I don't really know where that is. I'll just call it 2.5. I don't know exactly how accurate that is, but it's in between 2 and 3. And for a graph, in between 2 and 3 is about as good as you can get anyway. 3, 3. 4, 10. That is a weird graph. That is correct. Looks like it bounces off the x-axis there. Does anybody see what makes it bounce off the axis based on those equations up there? Any thoughts? The absolute value. Absolute value, this means y is going to always positive. So when we were going to have negative values, which was going to happen over here, it bounced them to the positive side and made everybody positive. So that's kind of a weird graph, for sure. Which probably means that when we find the rectangular equation, by eliminating the parameter, it's going to be kind of weird. So let's see what happens. So we'll start with the x, because our goal is to get y equals something of x. So let's solve for t. Let's see, we can square both sides. It gets us x squared equals t plus 3. Move the 3 over. So there's the parabolic looking thing. That's kind of why it's curved, maybe. And then we'll plug in x squared minus 3 in for t. Absolute value of x squared minus 6.
Well, actually, can't you back to that? But why wouldn't x squared minus
I can't factor it. If it was x squared minus 9, I could factor it.
Oh, yeah, yeah.
This does not turn into x squared plus 6 because you have to take the absolute value after you do x squared minus 6.
I see.
So there's nothing more I can do with that.
Why wouldn't it be x squared minus 3 in parentheses? And then minus 3.
So why wouldn't it be? Is that what you mean?
Yeah.
Is that what you said?
T equal that.
That's fine. And then minus 3 more would be minus 6.
Oh, yeah.
Now this you could put in the calculator if you wanted to graph it and see if that really matched what we think it is. And it does. And you won't have a calculator anyway. But once you get it to y equals x stuff, then it becomes more normal. All right, page 2. And by the way, I gave you notes 1 and 2 at one time here, so we're almost done. Once we do this one. Yeah, well, just be careful. It is all we're doing, but that's a lot of blanks on that page. It's a how well do you know your unit circle problem. That's for sure what it is.
This is a nightmare.
So x is 4 sine t, and y is 2 cosine t. You know, you don't have to put that above those, but it may be helpful to keep it straight. And again, it's rather than going xy, 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 and jumping back and forth, sine, cosine, let's do all the x's first. That way our brain is on the sine function, then we'll switch our brain to the cosine function. I'm going to draw a unit circle here, or at least part of a unit circle. It helps me think about this. So what's the sine of 0? 0. Pi over 6. I'm going to put them all in this unit circle because, one, it helps me answer this question, but it's also going to help me answer the next column as well. So I may as well put them on here. What's the sine of pi over 6? 1/2. Pi over 4 is that middle one. Root 2 over 2. Now, let's do a little bit of work in our head here. The 4 and the 2 reduce, and that gives us 2 root 2. And most of the time I don't know what 2 root 2 is, but there's some helpful hints right here. 2 root 2 is 2.8. We don't need 3 decimals here, right? Because we're using this to graph. There's no way you can tell the difference between 2.8 and 2.828 on this graph. Like, you're just not zoomed in enough to be able to do that. Let's see. Whoops, already filled in the answer there. Sine of pi over 3. Let's see, that would be root 3 over 2. Uh, 2 root 3. Again, I'd be stuck, except they gave me a helpful hint over there. 3.5. Sine of pi over 2 is 1. So that's 4. I'm going to press pause, and you see if you can finish the x column. All right, now let's go back and do the y's. That's 2 cosine. So 2 cosine of 0. So I've already got my angles there. I just need to make sure I look at the right one. What's the cosine of 0? 1. Whoops. So 2 times 1 is 2. The cosine of pi over 6. Root 3 over 2. The 2's cancel. I'm left with root 3, which is conveniently right there in the box as 1.7.
Is it going to be like that on the test?
Yes, we would give you the weird ones. Let's see, cosine of pi over 3, that's 1/2. Cosine of pi over 2 is 0. I'm going to press pause again and let you do some unit circle review. We'll check and see. And then step next is to graph all those points. But that's easy, right? X and Y, so you don't need t anymore. We just need to graph all those x's and y's. So 0, 2. 2, 1.7.
Will there be like one of these in the test where like it like has the table and then the graph? Like I'm guessing.
Yes.
So then like will we be wrong if we just put the answer for the table, or like do we have to put like the math that you did?
No, you wouldn't need to show. Like if you could do that in your head and just get to the answers, that would be fine. Put one of those points on there wrong. And so we play connect the dots and connect them in order now, right? Because there's an order to this thing.
So it connects full circle?
It does, because it started at 0, 2 and it ended at 0, 2.
Well, it's using the unit circle.
Because you're using the unit circle, so it kind of makes sense that it might start repeating itself. Mathematical name for that shape? Ellipse. Yes. I mean, yes, it's an oval, but I had second period what that shape was, and I got oval and football, and I was like, how about a math name for it? Let's call it an ellipse. All right, part C. Find the rectangular equation by eliminating the parameter. X equals 4 sine t. Now, don't try to race ahead of me on this one because we're going to do something different here. If I want to solve for t, what should I do first? Divide by 4. And then we're taking the sine of t. So don't write it down, but if we wanted to undo that, how would we get t by itself?
Inverse sine.
Inverse sine, good. You don't divide by sine, you would inverse sine. But that would really get weird, because then I'd have inverse sine of x over 4, and I'd plug that in, and that. Let's hold off on that for a minute. We're going to try something else. Y is 2 cosine t. So y over 2 is cosine of t. Now, if only there was some standard equation that related sine and cosine.
Oh,
Yeah,
There is.
cosine squared, sine squared equals 1.
Yes. Usually we put it the other way, but what you said was right. Sine squared plus cosine squared is 1. That's always true. So we're going to get kind of sneaky here. In place of sine, I'm going to put x over 4. In place of cosine, I'll put y over 2. So x over 4 squared plus y over 2 squared equals 1. So x squared over 16 plus y squared over 4 equals 1. Do you remember from those equations what shape that would make? I mean, the answer is kind of already there in the problem. That makes an ellipse. That's right, it makes an ellipse, a football, an oval. Where we would go, so how many left and right would we go? Do you remember when we were graphing ellipses? You go left and right 4, and how about up and down? 2? And does that match with what our graph already had? Yeah. And so there's a connection between parametric and rectangular that we're able to kind of figure out. Now, we're not going to do this with calculators, but I want you to see it in case you ever need to. If you've got a calculator, grab it. Go to mode, and is there any, maybe you just saw what I just did. Do you see anything under mode that would match what we're doing now?
Yes. Agree. Yeah.
We want to be in radians.
Yeah.
PAR is not par like golf, but parametric. So put it on par for parametric. And then when you go to y equals, it doesn't really give you y equals. It gives you x equals and y equals. 4 sine t and 2 cosine t. And if you graph it, you get the ellipse. And it also graphs it in order. This is kind of, if I change my window a little bit to make it do it again. Like, watch when I hit graph, it will graph it in order. Like, usually you don't pay attention to the order because it doesn't matter, but since this one has an order, it graphs it in order. Actually, you can slow the order down too over here. Kind of slows it down and traces it out for you. This is also for people who like messing around with their calculator. This is a place to get some weird graphs. If you start changing things up, you can get some goofy looking things going on. I don't know what just happened. I mean, I know what I did. I added t, but I didn't. So parametrics create some weird. So if you're, it's like the old spiral graph kind of thing. All right, let me give you the worksheet.